Now we are going to learn the derivative dy upon dx for common functions. Okay, as we earlier saw, dx is a very small value, so we are going to neglect it, kind of neglect it. Okay, now see, for x raised to power n, for this expression, for y equal to this, we have d, we get dy upon dx as d x raised to power n upon dx, exactly like this. Okay, now this is equal to n x raised to power n minus 1. This is exactly because earlier we saw that the slope of tangent at a point, at this point A, this is the curve that represents the graph of yx. Yeah. So at this point, this is the point that lies between two very close lines, and between these the value of delta x is very small. Now here, if we move these two lines very close, we will eventually get just the point A, that is the point of contact between the tangent and the curve. This actually represents instantaneous rate of change at point A. Instantaneous rate of change. Now why this matters? Because by definition, derivative of function x, okay, we are not going this much deep, but there is some derivative formula, and from that we derive that for this we will derive this. Okay, so we will go in a little bit detail only. Derivative of fx is equal to fx plus h minus fx upon h. Now at h equal to 0, these points are these two lines are very close and represent point of contact at A, and we know that point A is representing instantaneous rate of change. Now since fx is equal to x square, for now, we are going to represent fx as x square. Now fx plus h is we are squaring the whole term, so we are going to square this also. Function of x plus h whole square, we are going to get by squaring these two terms like this, x square plus h square plus 2hx. At h equal to 0, these two terms are going to be nothing, no, not like that. Actually, this x square cancels with this x square, and we are left with 2xh plus h square upon h. Taking h to be common, we get h common from here, 2x plus h on h, we are going to get 2x plus h. Now h equal to 0, h approaches 0 because the length between these two lines is 0. So we are going to get 2x, that is x raised to power 2 is equal to 2 multiplied by 2 minus 1, that is just 1. So our next common function is going to be the Euler's number raised to power x. Now we don't need to go in much detail, so we are just going to, okay, this is equal to just ex. This is a special property of the Euler's number. For those who don't know, Euler's number is a special number. It is represented by e and is equal to 2.7 something. So this is a very special case because derivative of Euler's number raised to power x is equal to the Euler's number raised to power x only. This is actually an exponential number. It appears in exponential, etc. This is its amazing property. It is derivative of itself. And next we are going to see natural logarithm in x. It is represented by ln x. So derivative of this on dx is equal to 1 upon x. This is a simple relation and we just need to memorize this for calculations and numerical problems. Next we are going to have, okay, we may firstly understand these two, why these two occur. For Euler's number, this actually appears in exponents, and we know that exponential growth looks like this. This feels similar. The graph of this is going to be this only. It's going to be like this only. So E is the one of the special base, and for E, its exponential growth matches with its own growth. Its exponential growth matches with its own growth. So this is just going to be equal to itself. This, okay. Next we have natural logarithm. Actually, natural logarithm of x is the inverse of Euler's number raised to power x. That means this is equal to x. Okay, we can also write, okay, these are the rules that come in logarithms, etc. We are going to catch up to that later. This we are just going through like just a simple reason why does this exist. Euler's number raised over x equal to x. They undo each other because e raised over x has special derivative property. Its inverse gets a clean derivative, just like this. This is a clean derivative. There is no complex calculation or something like that. Simply speaking, as we had learned that this of ex is equal to ex, we know that x is inverse of ex, so the result is just going to be inverse of x. This would represent a graph that looks like this. This starts at 1 and slowly it gets flatter and flatter. This is the inverse of this. We are going to get a deeper understanding after learning about graphs and functions. So next we are going to move on to trigonometric functions. They are quite simple to memorize. So firstly we have d d of sine theta upon dx is equal to cos theta. I'm just going to write in a summary. For cos theta is equal to minus sine theta. Just check what it is. For tan theta we have sec square theta. For other t ratios like cosec theta, we have minus cosec x theta cot x, and for sec x theta, for sec theta we have sec x tan theta, and for d cot x, actually we shouldn't be writing theta here. We should actually be writing x because of this. Okay, so because we are learning these are functions of x, these are going to be functions of x, so we need to write x. Sorry, my bad. We are just going to let theta equal to x. Okay, upon dx is equal to minus cosec square x. These are the 6t ratios. These are the differential coefficients of y with respect to x for the 6t ratios, and that's it. We have learned different values of dy upon dx for different functions. So in the next lecture we are going to see a few numericals and try to solve them. Keep the momentum going on.